Have you ever wondered what happens to the laws of physics when two black holes collide? Do the old theories still hold, or do we need to rewrite everything from scratch? Now imagine one of the most powerful cosmic collisions in history has occurred, and scientists have managed to record it with unprecedented precision. This video is about the moment science pushed its boundaries and challenged, then confirmed, a 50-year-old theory by Stephen Hawking. Stay with us till the end, because this story isn't just about space, it's about the future of our understanding of reality. If you think physics is just formulas and numbers, this video will change your mind. Here, we're dealing with waves that emerged from the heart of absolute darkness, waves that not only ripple through space-time but shake the foundations of scientific theory. This is the story of two cosmic giants colliding, and the moment science heard their crash. Nearly 10 years after gravitational waves were first detected, scientists have now confirmed Hawking's 50-year-old theorem by recording the strongest waves of this kind ever observed. Thanks to major advancements in gravitational wave detection, astronomers were able to identify waves from an extremely powerful black hole collision as they passed through Earth at the speed of light. This breakthrough allowed them to successfully test Stephen Hawking's 50-year-old theorem about black hole mergers. In 1971, Hawking proposed his black hole area theorem, which states that when two black holes merge, the event horizon of the resulting black hole, the boundary from which not even light can escape, cannot have an area smaller than the sum of the two original black holes. This theorem reflects the second law of thermodynamics, which says that entropy or disorder within a system never decreases. Black hole mergers distort the fabric of space-time and create small ripples known as gravitational waves, which can travel across the universe at the speed of light. 5 gravitational wave observatories on Earth search for waves that are 10,000 times smaller than the nucleus of an atom. These observatories include 2 LIGO detectors in the U.S., Virgo in Italy, Kagra in Japan, and GEO 600 in Germany. They are operated by an international group known as the LVK Collaboration. The recent black hole collision, named GWT 150114, is similar to the one that produced the first observed gravitational waves in 2015. Both events involved black holes with masses between 30 and 40 times that of our Sun and occurred about 1.3 billion light-years away. This time, upgraded detectors at the Laser Interferometer Gravitational Wave Observatory, LIGO, had 3 times the sensitivity compared to 2015, allowing them to record the collision waves with unprecedented detail. This enabled researchers to calculate the event horizon area after the merger and confirm Hawking's theorem. Laura Nuttall, a researcher from the University of Portsmouth and member of the LVK team, says, when black holes collide, they produce gravitational waves that, like a ringing bell, contain overtones or harmonics. Previously, these harmonics would fade too quickly to be clearly identified, making it impossible to calculate the event horizon areas before and after the collision, a key requirement for testing Hawking's theory. A 2021 study on the first detected collision confirmed the theory with 95% confidence. The new research raises that confidence to 99.999%. In the 10 years since scientists began detecting gravitational waves, around 300 black hole collisions have been recorded, but none as strong and clear as GWT 150114, which is twice as powerful as any previously detected wave. When GW 250,114's gravitational waves reached Earth, only the LIGO observatory was active among the LVK collaboration's detectors. This didn't affect the test of Hawking's theory, but it did prevent researchers from pinpointing the exact origin of the waves in the sky. Ian Harry, a researcher from the University of Portsmouth and LVK team member, says, future upgrades to LIGO and other planned observatories will have greater sensitivity and allow us to dive deeper into black hole physics. We may not catch every collision, but we'll see another event like this. He added, with the next round of upgrades, maybe by 2028, we'll see something similar, and by then, the sensitivity might be high enough to truly examine the details. These recent findings pave the way for new research in quantum gravity, a theory physicists hope will unify general relativity and quantum mechanics. Nuttall says the results show that general relativity and quantum mechanics still work well together, but some discrepancies may emerge in the future. Recent LVK data also allowed scientists to confirm equations proposed by New Zealand mathematician Roy Kerr in the 1960s. These equations predicted that black holes can be described using just 2 parameters, mass and spin. In other words, 2 black holes with the same mass and spin are mathematically identical. Thanks to GW 250,114 observations, we now know this is true. In a universe where every moment can unveil the secrets of existence, black hole collisions are no longer just cosmic events, they're bridges between classical theories and the future of quantum physics. Confirming Hawking's theorem with 99.999% accuracy isn't just a scientific triumph, it's a sign that we're on the brink of discoveries that could redefine our understanding of reality. So next time you look up at the sky, remember, out there, a collision might be shaping the future of science.